Today we are going to perform the experiment torsional pendulum. The aim of the experiment is to determine the moment of inertia of a body by means of a torsion pendulum. For this we need the apparatus, the torsion pendulum. This is the torsion pendulum. Then we need the spirit level. This is the spirit level. We need the stopwatch. We have the stopwatch. Then we need the heavy rectangular metallic mass. This one is the heavy rectangular mass block. And this one is the heavy circular metal block. We also need the knitting needle, which is there at the crater of this moment of inertia table for balancing this apparatus to make it perfectly horizontal. And we need the slide caliper. This is the slide caliper by which we will be measuring the diameter of this metallic block, circular block, and this rectangular block, the length and breadth of this metallic rectangular block we need to find out by the slide caliper or vernier caliper. So, what we need before starting to take the reading, we need to make the torsional pendulum. This one should be perfectly horizontal. So let us make this one perfectly horizontal. To make it perfectly horizontal, let us put this spirit level at the center of this table, actually at two perpendicular directions. One is this. So if at this position, if the bubble is there at the middle of the spirit level, which is exactly at the middle, and at its perpendicular direction, like this, if we place, and if it is still at the middle of this spirit level, there is a bubble, and we can see that bubble is there at the middle of the spirit level. So we can enlarge, we can see the bubble is there at the middle. So in both the directions, in two perpendicular directions, the bubble is there at the middle of the spirit level. It means that the moment of inertia table is perfectly horizontal. So after that, we will be removing this spirit level from the torsional pendulum. Now, what we need to do, we have to give 25 oscillations for this table. So we are going to oscillate it. We will be oscillating this table in such a way that its angle of oscillation will be very small, and there will not be any other movement like this sort of shaky movement, or this sort of movement will not be there. The movement will be purely rotational, means there is an axis of rotation, this wire from which it is hanging, this torsional pendulum, it will be rotating about, or it will be oscillating about this axis of rotation. This is the axis of rotation. Okay, so no other motion will be there. If there is any other motion, then that will be give some problem in the result. So let us move this table by very small angle. Let us see if we can okay, let us check. I'll be giving very small oscillation. It's not observable. Yeah, from this point. So let me oscillate it by holding it to a position, stationary position. Let us first make it very stable, and after that we'll be rotating this table by very small angle. Let us say this much. Okay. After that we'll be leaving this torsional pendulum. There is some shaky movement is there, vibratory motion is there. So we don't want all this vibration. We want pure rotation. So simply we'll be rotating and we'll leave it. Let us see what is happening. We will not start taking the reading immediately after making it in the rotational position. So we will wait until we get the stable situation, means when it will be in oscillation, means in rotational motion, there will not be any shaky movement, means this sort of movement will not be there, rather it should not be something, it should not move around the axis of rotation. So this is the ideal condition when we can take the reading. So to start the reading, what we will be doing, this is our stopwatch, will when this end will go to one particular end, let us say here will start. So when it will be going and once again it will be coming back to the same position, let us say to this particular end, okay, over here, yeah, 1. So like this 25 oscillations we need to count. Okay, let us see, this is 2. We are going to take 25 oscillations, and you must have the patience to count these 25 oscillations and very carefully, because depending on this time period you are going to find the moment of inertia. So 3, this time it is 4, and 5, six, 7, 8, 9, 10, 11, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and this time it is going to be 25, and moment we will get 25th oscillation, we will stop it. So I have to 25th stop. So the time we have got for the empty table without giving any block, rectangular or the circular block, we are measuring the time for 25 oscillations. So you need to repeat this 25 oscillations 3 times, and then for this 3 times 25 oscillations mean altogether 75 oscillations. So time taken for this 75 oscillations divided by the total time. Suppose this time it is 5 minutes 24 second 0.59. So this is the amount of time required for 25 oscillations. And next time suppose you are getting to 5 minutes 23 minutes point something second. So you will be considering that, and then next time suppose you get 5 minutes 25 second point something. So altogether you add up all these 3 times and divide it by 75 to get one oscillation time period. That will be your time period for the empty table. Okay, if you go to your table, then you will understand. Okay, now so those 2 more 25 times I am not going to take. I will be providing you the data by which you will be calculating. And next one is to put the metallic circular block. Okay, so I am going to put this metallic circular block So, and I am going to repeat this experiment. This one is known one. Okay. It should be the center of this circular block must be at the center of this empty table. That should be carefully noticed. Okay, now I need to repeat the same thing, means I have to rotate this torsional pendulum by very small angle, and then I need to leave it. So it will be in oscillation, 25 oscillations I need to calculate, 25 oscillations. So I have got for the first set of reading, the empty table, I have got 5 minutes 24 second 0.59. It is 100 part of a second. So let me write it down. Minutes 24 second 0.59. Now for the table, in the second for the table we have this table for time taken for 25 oscillations of table and the rectangular body, that is having the time period small t1. Okay. So no matter, our aim is to find the time or the time period of this table, and the last one is to the time taken for 25 oscillations of table and the body whose moment of inertia to be determined. Actually, the moment of inertia of this circular metallic block is to be determined. So we should put that one at the last, but since it does not have any relationship with the time period of the other one, means the metallic block, this is, we'll be considering this one as the known one, and this is the unknown body. So knowing the moment of inertia of this metallic block, we can calculate the moment of inertia of that one. So since we have put this one, so we'll be taking the time period for this one. Again, we are going to set our stopwatch. Let us reset our stopwatch. This is the reset button. If you can notice or if you can see, it's not focused, but over here it is reset and split is written. So let us reset it, and then when it will be like in the last one, when it will come to this end, we will start. Okay. Moment it will start going this side, start. So our time starts already, and when it will be coming back to the same position, our one oscillation is completed. So it is 1. So this time it is 2 oscillations. So we need to calculate time for 25 oscillations. So this time it is 3. And remember, this one will be more than the previous one. This is 4. Fourth oscillation have been completed. This time it is going to be 5. So it's 5. Actually it is time consuming experiment. This time it is 6. And it is 7. Eight. 9. 10. 11. 12. 13. 14. 15. 16. 17. 18. 19. 20. 21. 22. 23. 24. So at 25th we are going to stop our stopwatch. It is going to be 25th. Yes, stop. So our time is for the 25 oscillation 5 minutes 37 second 0.78. Okay, let us write this value. And this one will be on which column? It will be on this column. If you go to your manual, it is the time taken for 25 oscillations of table and the body whose moment of inertia to be determined, T2, okay, in second. So in minute whatever reading we have got, we are going to write that one, 5 minutes 37 second point 78. We need to convert this one into second, okay, 5 minute 37 second point 78, that we need to convert it into second. So at last what we are going to do, actually this reading for this rectangular block should be taken before this. Since we have already taken this one, so at last we are going to take the measurement for 25 oscillations for this metallic rectangular block. Okay, so I have to take out this and this should be placed exactly in the middle in such a way that the distance from this end, it should be same as this. The axis of rotation must pass through the center of mass of this rectangular block. If it is not placed properly, you will not be getting the reading, the proper reading, means you will be getting faulty result. So once again let us rotate it by very small angle. Let us rotate by this much angle and leave it. So when we will get stationary, means the oscillations are very much stable. So when there will not be any shaky movement or vibrational part will not be there, we will start taking our readings. So once again I am going to reset the stopwatch. Okay, so reset 00. Moment it will go to one experiment, this time start. So I have started taking the time period, this end. Once again when it will be coming back to its same position, one oscillation is completed. Yeah, one is gone. So it is going for the second one. So let us count this 25 oscillations for this. 2, 3, 4, little bit shaky movement is there, so if we can system 5 can eliminate that shaky part, it would be better. This time it is 6. Seven, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have got for this rectangular block 25 oscillations. Time is equal to 5 minutes 30 seconds, 0.40 is the time. So let us write this value 5 minutes 30 second 40. So we have got all the values for 25 oscillations. For this column is for the empty table, this column is for the rectangular block whose moment of inertia is known. Okay, for 25 oscillations it is 5 minutes 30 second 30.40, this much of second. And for the last column, the moment of the time period for the empty table plus the circular block, circular metallic block whose moment of inertia is to be found out. Now, as I said that the moment of inertia for this column, for that means the rectangular body, the moment of inertia of this rectangular body is already known, or it is known. So how to find the moment of inertia of this body. That we need to apply the formula, but before that I want to tell you, you need to complete this table by taking 2 more set of readings. Means for the empty table there should be 3 set of readings, 25 oscillations, 25 oscillations and 25 oscillations. And for this similarly, for the rectangular block also, I have taken 1 set of reading for 25 oscillations, but altogether 3 sets of reading should be taken, and the average should be found out for that. And for the last column, again 3 sets of reading, 25 oscillations, 25 oscillations and 25 oscillations, and then you need to find out the average of this, all these 75 oscillations. Okay. So as I told you, in the calculation part you will be finding for the 75 oscillations, you will look at this value of this 75 as because 3 times 25 oscillations means 75. So whatever time, total time, means you will be getting 25 oscillations for this. You need to convert this minute into second. So okay, 5 minutes is equal to 560, 5 into 60 is equal to 300 minutes, 300 seconds. So 300 plus 24.59. So that will be your 324.59 seconds will be the time for the 25 oscillations. So you have to add all these 3 times value, that means for 75 oscillations, and then that total time will be divided by this 75 number or the 75 oscillations. So it is total number of oscillation is equal to 75, as you can see over here. So that is how you will be getting the time actually. This time, capital T, is the time period for the oscillation of the empty table. Similarly, T1, capital T1, is the time period of oscillations for the rectangular block and the empty table. And capital T2 is the empty table plus the circular metallic block time period. Okay, so that is how you need to find out the time period. And in this column, as I have already told that we are measuring the oscillation for the body whose moment of inertia is already known. So for the rectangular body, how to find the moment of inertia, that I am going to tell you. So this is the rectangular body and its mass is given 635 gram. And to find the moment of inertia of this body, we need to measure the length and breadth of this rectangular block. Okay, so the length of this one we can measure by this vernier caliper. We can measure it like this, so we can see the reading from here. I can tell you the value, which is the length is equal to 5.9 centimeter. 5.9 centimeter. Okay, the length 5.9, and the vernier scale 5.934. You cannot see it properly, but 5.9. It is exactly matching with 5.9. So we'll be taking this one as 5.9. If you can see, this value is 6. So just before this 6, the vernier 0 is matching with the 5.9 centimeter line. So length is equal to 5.9. We are going to write over here for the second table, we are going to write the value of this main scale reading 5.9. Okay, 5.9. And the vernier scale, vernier division is equal to 0, hence the total value will be equal to 5.9 centimeters. Oh no, this one is for the second table, actually for the determination of the circular disc. So we'll fill up this second table later on. Since our known body is this rectangular mass, we are measuring the length. So if you can see, the length is written over here, length of the rectangular body, capital L, which will be equal to 5.9 centimeters, right? We also need to calculate the breadth of this one, length and breadth. So breadth is for this body, the breadth is this one. So let us measure the breadth. As I can see, the breadth is 4 centimeters, exactly 4 centimeters. Okay, look at this. Not properly focused, but this value is 4. This value is 4, and which is matching exactly with it. So the breadth, I'm going to write 4 centimeter. Mass, the 4 centimeter, I have written over here, this 4 centimeter. Mass, you can write it from, which is written on top of the rectangular block, 635 gram. So 635 gram. So applying the formula, this I1 is equal to mass into length square plus breadth square divided by 12. You will get the I1 value. You will get the I1 value. And to calculate the radius of the circular disc, what we need to do? We have to measure the diameter of this circular disc. Okay, let us measure the diameter. So like this, you can measure the diameter. The scale should pass through the center, and you can measure the diameter something like this. Okay, when the scale will be perfectly through the center. Then once you measure the diameter, it is, let me see how much is this. This is equal to 10.1, and the vernier scale reading is equal to 4, 10.1 centimeter. So I am going to write 10.1, and the vernier scale reading is equal to 4. Since the vernier constant is equal to in terms of centimeter, it will be 0.01 centimeter. So, Vernier scale reading multiplied by the Vernier constant will give you 0.04. So, your total reading will be 10.14. So, look at the table. 10.1 is your main scale reading. Your Vernier scale reading is equal to 4. So, Vernier scale reading value is equal to 0.04. Total reading will be equal to 10.14. You have to take 3 times the same reading at different directions. So, after that you will be taking the average of all these 3, and then after getting the average diameter, you will be finding the radius of that diameter. So, simply half of that. So, if I take for this particular value, it will be 5.07. So, 5.07, 5.07. Now, all my values are there. If I put all these values in the formula, then I'll be getting the I2 value, I2. I1 I'll be getting from this formula. So, I'll be putting this I1 value over here, and from the table 1 I'll be getting the value for this time period, capital T, capital T1 and capital T2. These are in second. So, that value I'll be putting in this formula for this T2 square minus T square, T1 square minus T square. Okay. For this ratio, I'll be putting the value of T, T1 and T2. That is how I'll be getting the value for this moment of inertia I2. That is the experimental one. I have another way to find out the moment of inertia theoretically, and theoretical value I'll be putting the formula for the disk about the axis of rotation, which will pass through the center of the circular disk and perpendicular to the center of disk, perpendicular to the plane of the circular disk. So, that value is given by half mc. mc is mass of the circular disk into r square. R value I have found out from here, and mass of the circular disk, that is written on top of this circular disk, which is equal to 650 gram. So, put all this value, and then you will be getting the one value which may not be same as the experimental value, which just now or just before this calculating this theoretical value you have calculated. So, that experimental value may be different from the theoretical value. So, considering the theoretical value as the standard value, you need to find out the experimental error or percentage error. So, that error you will be getting applying the formula I2 theoretical minus I2 experimental divided by I2 theoretical, because theoretical is more perfect, and that should be the value, and then multiply it by this 100%, and these things are there within the mode symbol, as because this, if I2 experimental is more than the I2 theoretical, in that case it will be negative, but you need to take the magnitude of that value. So, whatever percentage error you get, it should not be more than 30% error, and in the result you can say that your experimental value is this, and with the percentage error is this. So, after that you can go for the discussion part where you write the sources of error and the analysis or discussion. So with this, this experiment will be over. Here I want to tell you one thing, even though I have taken one set of reading, with this one set of reading, even though the experiment can be done, but only one set is not good enough to complete one experiment, hence 3 sets of readings are required. We will be providing you the data and you need to calculate all the necessary calculation you have to do and you have to send us the results. Okay, thank you.